This is Physics 2212, Lab 2, Lines of Charge. Our purpose of this lab is to improve on our previous model by making the tapes be a line of charges rather than a point charge. And as for our results, the electric force was very close to the gravitational force, with the electric force of the tape being 1.122 e to the negative 3 newtons, and the gravitational force was 1.993 e to the negative 3 newtons. And I calculated the charge of one tape, and it was deemed to be 3.533 e to the negative 9 coulombs. The physics principles of this lab would be superposition of electric field, Newton's second law, F equals ma, and Coulomb's law for force of one object on another object, which I use in this little sketch here. I derived of an equation to calculate the charge Q, which is how I got that previous value of 3.53 e to the negative 9. Models and assumptions are the same as Lab 1, but the tape is assumed to have an evenly distributed charge across its surface. We assume no air resistance, no wind, no external electric field, etc., etc. Our model also considers the tape to be a line of equally spaced point charges of equal charge. Same idea as the first point. Models on the right there. You can see the tape. The two tapes are separated by distance d, which in our code is viewed as R. The system, of course, is tape B, and the surroundings are tape A and the room. And the process is the same as Lab 1. My data is carefully documented, so I don't need to go into the steps of how I got that experiment set up. Here's my code in the top segment. You can see that I initialized the top tape and the bottom tape as line charges using a function given to us by the instructor. If you look carefully, you'll see that I gave these tapes the same mass and the same charge as the initial conditions from Lab 1. And then in the second block of code, I used two for loops, one for the top tape and one for the bottom tape. And the idea is to initialize an electric field vector for the top tape, and then to have each individual point charge for the bottom tape contribute to that electric field for the top tape. And as it keeps iterating through and through, we get a much more accurate measurement of what the electric field at the top is due to the bottom tape. And in that last line, you can see that I just multiplied the result by a predetermined scalar. And that is just so the visual that we generate is actually, you can actually see it, because we're working with really, really small things here. Perfect segue. This last section of my code is the visualization portion, and I essentially just graph the electric force vectors. You can't see the white one for some reason, but it's there. It's essentially the same in magnitude as the yellow arrow, but it's opposite in sign. But you can't see it because I used so many green arrows for the electric field, like the individual electric fields, and that's just to really get a good visual of what the distribution of charge looks like. But yeah, and this is essentially, you can see that in the bottom right, you can see the output shows that the magnitude of the electric force was roughly the same as the magnitude of the gravitational force, which follows Newton's laws, specifically Newton's second law. As for similarities and differences, the electric force and the gravitational force were still roughly the same, Newton's second law. However, the line model charge was in fact one order of magnitude smaller than the point charge approximation. Now, what if you had modeled each of your tapes as a single point charge, like in the previous lab? Well, the charge would have been one magnitude larger, as we saw. But why do these estimates differ? Which value is more likely to be closer to the real value, and why? Well, the line charge model is the sum of multiple point charges. Thus, its result is more thorough, and it accounts for the surface of the tape along the x-axis. Think about the first lab, where we just had one single point charge. You can't account for the length of the tape that way, since you reduce it all to one point charge. Whenever you reduce things to a single point charge, your approximation suffers. This model is much more accurate because we don't reduce it to a single point charge. We treat the tape as a line of multiple point charges, which is significantly more accurate compared to a point charge approximation. As for conclusions, this model is really cool. Despite being more advanced, it still follows Newton's laws. You see that the forces were roughly the same, as in the magnitude of the electric force and the magnitude of the gravitational force. But One thing that I noticed, it does have its flaws. Whenever you vary the distance between the two tapes, it produces very weird results, either if you make it too far or too close. I tried making it really close to zero, and the arrows just got really wonky. I don't know, you can try it yourself, but that's what I noticed. Thank you so much, and have a great day.